Hello, lovely human. Welcome to STEM Bites, where we talk about seemingly simple questions in science, tech, engineering, and math. Woo! Yay! Okay, we have a return of our favorite bird that can't fly, physics penguin. Yeah! Okay. All right, physics penguin, what question do you have for us today? What is the most or coolest particle in the universe? Oh, wow. All right, well, the coolest particle in the universe is definitely a matter of an opinion. So I will give you my opinion because I have a very strong opinion on this topic. So I think the coolest particle in the universe is the electron, which is symbolized with a lowercase e and a little minus sign because it is negatively charged, unlike its antimatter cousin, the positron, which is positively charged. There's a joke in there somewhere. Moving on. So there are 4 reasons why I think the electron is the coolest particle. I will go over them quickly because I know some of y'all are busy and want to bounce, and then we'll go into them in a little bit more detail for those of y'all that want to stick around and learn more. Yeah. Okay, so the quick version. Number 1, the electron is a true point particle. It has no volume, but it has mass. What does that mean? Number 2, the electron is one of the particles that's largely responsible for the electromagnetic force, which is light. Yeah. And also electricity and magnetism. Electromagnetic. Ha. And so electrons are responsible for the fact, or partly responsible for the fact, that we can see all of these different things around us. And they are responsible for the fact that we can touch things because electron clouds, repelling electron clouds and other atoms, is why we don't fall through the floor and why we can clap. Very important things. And why we get to pet soft things like dogs and bunnies and say hi to plants very gently. So, rad. Number 3. Okay, electrons are all identical, which is wild. They all have the same exact mass. They all have the same exact charge. They all really look the same. Mind-boggling. And finally, number 4. Hold on, I gotta look at my notes. Oh yes, okay. They truly represent the wave is a part the wave particle duality, wave and a particle. And with electrons, we deal with them so much with electricity that this wave particle duality actually comes into play with some of the things that we invent. For example, electrons can tunnel in chips because we've built computer chips. ICs, integrated circuits, are so small now that electrons tunneling because of their wave particle duality is actually something we have to keep in mind. Okay, boom. That was the fast route. I hope I did it fast enough. Let's go into a little more detail, and I'm going to write them down because yes. Okay, so number 1, point particle. Point. So what does that mean? Well, I mentioned briefly that, yeah, they don't have volume, so they don't actually take up any space. Even if I were to draw a dot on this 2-dimensional surface, it still is taking up space, and that doesn't totally represent what a point particle is. So we can measure it, and we can see it in certain ways, but it doesn't take up space, and that is mind-bogglingly cool. Number 2, let's go with a color that looks good next to red. Okay, let's go with purple. Okay, so number 2 is the electromagnetic force. So like I mentioned, this is how we are able to see, well, pretty much everything that we can see. So I'm just going to say vision. So what happens is a photon of light comes in to an atom and it collides with an electron. It transfers its energy. The electron goes, whoa, I have more energy. It jumps up. Or if you've seen the electron bands, you can think about it like that. So a photon comes in hits an electron here, the electron jumps up to a higher level energy band, and then when the electron drops back down, the atom emits another photon of light, and that is how we see objects. Isn't that so cool? So sunlight uh, would be a source of photons, or the light above me, or my desk light. Those are all sources of photons. Or back in the day, we'd have torches and candles and all of those good things giving us photons so that we can have this interaction, this exchange of energy between the photon and the electron to actually see stuff. So cool. Oh yeah, and then the photon goes to our eyeball. That's an eye. Give our friend some nice little eyelashes and maybe an eyebrow. It's an eye. Huh. So photon goes to the eye, we see things. Cool. For touch, we have these electron clouds that are repelling each other, and I'm very much simplifying here. But basically, we can touch things because of the electromagnetic force, because of the electric repulsion between electron clouds in different atoms and molecules. So rad. Okay, number 3. All the same. So this one has a silly story associated with it that really tickles me. So physicists were so mind blown that electrons, every single electron that has been detected and measured and recorded, have the exact same mass with these hilariously large number of significant figures, like 10 or more, very, very, very precisely. Same exact mass, same exact charge, they look the exact same. Wild. And physicists were so stunned by this that some of them actually proposed that, well, maybe there's actually just one electron moving, zipping forwards and backwards in time really, really, really rapidly. That's not true. That was a hypothesis that was effectively disproven. But I love that. The fact that electrons spooked physicists so much because they were so identical that they were like, well, maybe there's only one? Because people are very different, right? Most of the things that we experience and deal with are very different. Electrons, all the same. Ha, so cool. I'm sure they're unique in their own way, though. Okay, and finally, we have electrons representing the wave particle duality just spectacularly, because when we're talking about electricity, we typically talk about electrons as in the particle format. There's a lot of the wave properties that come into play, especially voltage when you're talking about that. But a lot of times we can map a circuit effectively. We can kind of zoom out and say, well, if we say that the electrons are behaving like particles, we can mathematicize a circuit and kind of diagram a circuit out to understand what is happening in that circuit. But then we have things like electron tunneling, when we get to really, really small scales. And now we have to actually deal with the fact that the electron can also be a wave. And then the way that I drew this atom, where you have the nucleus in the center and then the electron cloud around, is actually kind of how you're supposed to draw it, because the electron exists as a cloud instead of at a predefined point in space. They still exist at certain distances, but it's a cloud of probability within that distance. So basically, like, let's say that this is the nucleus, and then you have some distance to where the electron can be, but you have a circle, right? And so the electron could be anywhere in this circle. And since we're working in 3D, not 2D, it's actually a sphere. Pretty wild, right? This is for a hydrogen atom also, by the way. Different atoms look differently, but they're a lot harder to draw. Chemistry students, y'all know what I'm talking about. Mad props for that. Okay, so Physics Penguin, I hope that this answered your question, and I hope I got you as excited about electrons as I am. Delightful. Okay, thank you very much for watching, and we'll see you next time. Bye!